So appreciate you all taking the time today to join our webinar, and we'll keep this lively and hopefully interesting and short so you can get back to your day. I know you all have things to be doing. So my name is Darren Hermans. I'm a product manager at Cambium Networks in the Enterprise Wireless Group. I work with the folks that do the enterprise Ethernet switching and the enterprise management, so we're all together as a team. Today we have a couple of my peers here with us to help us give us a better perspective and answer some better questions. Azif Abdul Salam. Azif, go ahead and introduce yourself.
Thank you, Darren. My name is Asif. I am as a principal solution architect working with Cambium Networks. Thanks, Darren.
Thank you. And Jonathan Scott, also we're glad to have Jonathan here as well. His perspective, he's a technologist. He loves technology, but he also works within our sales team. Jonathan, go ahead and introduce yourself.
Thanks, Scott. I'm the regional sales manager here for Cambium down in Texas, and I'm happy to be on the call and appreciate everybody joining.
Yeah, so we've got a wide range of experience. So let's go ahead and jump right in. Answer this question: how do we design a high density network? And so first of all, obvious question: what is high density? What are we talking about? And where can you find it? And so high density is really, it's a wireless network that provides pervasive connectivity. That means pervasive, corner to corner, every place, pervasive connectivity for all the devices within a defined space. So you define a space, it could be a classroom, it could be your business, it could be a retail shop. And then the density of the network is within that space. Capacity and density is the number of clients that are served by a single AP or network of access points. So it's the number of the clients and the data, the throughput required for the applications that the clients are running. So just look at a bit of a graph here, kind of average out some of the values. Look at logistics market. You see logistics has very low numbers of people per 100 square meters. So it's not a lot of devices, right? In a logistics warehouse, because it's about business, it's about moving boxes, and they have fairly low bandwidth. So that's for the far left-hand side of that scale. Enterprise and retail markets, they can have bandwidth anywhere from a 1 megabit to 10 megabits per second required, and density could be 5, 10, 20 people per 100 square meters, all the way in the education market, and you see quite a difference there as well. If you look at an average school application, the online schooling that the kids do doesn't take a lot of bandwidth per device, but there's lots and lots of kids, right? Lots of kids. Higher education, making more use of remote learning tools, and even within the environment, they expect high bandwidth, high bitrate requirements per device. And at the far right-hand side of the scale, you look at a stadium, a typical stadium, a sports arena. The seats are a little more than a half a meter wide, 20, 21 inches, 22 inches maybe wide. That's as wide as they get, right? They're not much. And then there's not a lot of space for each person. So yeah, you can get 150 to 160 people for every 100 square meters. And the bandwidth requirements are a little bit on the low side, the peak bandwidth requirements, but the numbers of people are very high. So when you start to look at capacity and density, look at those two factors: the number of devices times the applications that people are using. So a good high density network, what are we looking for? At the end of the day, there's three things that really stand out. And you will see this in every well-designed and operating high density network. You're going to see low transmission rates, low packet, sorry, let me say that again. You'll see low packet retransmission rates. Don't forget the RE there. So a retransmission is when a packet has failed, when it did not get to the intended destination, and the packet has to be retransmitted and has to be buffered and then retransmitted. And that's usually because there was an interference, there was a failure to receive that packet or acknowledge receipt of that packet. And so you get a high packet retransmit rate in poorly operated networks. So that's a characteristic of a well-operated network, is low retries. Low packet latency and low packet jitter. The jitter could be as low as 1 to 2 milliseconds. Nice consistency, you'll see that in a well-operated network. And then balanced data rates. So within the cell. So you don't want to see, what you don't want to see is a network where the access point is transmitting to the AP at 200 megabits per second at the RF data rate, and the client is trying to transmit back at 1 megabit per second or 6 megabits per second. That degree of imbalance in the data rates leads to lots and lots of problems in the network. So characteristics of a well-operating network. So those are 3 things you're going to be looking for. Today we're gonna skim across the surface of 3 things today, 3 keys to consider when you design the high-density network. We're going to talk a little bit about the throughput required to meet the applications, some of the typical numbers that you might see. We're going to talk about some of the SNR, signal to noise ratio, that you need to consider, and how that impacts the way you design the network. And we're going to talk about the configuration of the APs. Because APs from different wireless vendors are going to have capabilities that you're going to want to leverage. And so we're going to talk about some specific configurations that will help to improve and increase the density and the quality of a high density network. So first of all, make sure we know the applications. So understand the applications, know how those applications behave. Know how they behave. You'll oftentimes see people will sort of oversimplify this and say that, well, my total bandwidth is the application bandwidth times the number of clients. That's not it. That doesn't account for the whole story, does it? You can't say, well, I want to support 2 megabits per second per user, and I have 100 users, therefore I need 200 megabits per second. That does not account for the factors in the network. So understand and know the applications, know how they behave. Let's take a look at a couple examples here. Zoom, right? Today we're on this, GoToWebinar. A lot of people use Zoom. A lot of schools use Zoom. My son, they used Zoom at the end of last year. They're going to start using Zoom when they go back to school at the end of August. So if you look at a typical Zoom call, it's just a very typical Zoom call. And actually yesterday, I had my son set up a Zoom. He and I set up Zoom and Google Meet in our, we did some testing together, and we did some network captures. And he's 13 years old, so he doesn't quite understand all this stuff. But one of these days, he's going to appreciate all this education he's getting for free. But so we did some packet captures. We took a look at what does a Zoom call statistics look like. What is a characteristic of a Google Meet or Zoom? And what we found right there, very simple, a typical Zoom call is 360p. That's the quality of the call. That's the default. It does have a HD option, so does Google Meet. Up to 24 frames per second. But we also introduced some conditions, some congestion conditions, and we could cause that Zoom call to drop down to 10 to 12 frames per second, and it was still usable. It was still very, very usable, even at 12 frames per second, half that rate right there. And so that's an example of an application's behavior that you need to understand. You need to know that might default at 24 frames or try to get to 24 or 25 frames per second, but it really can be variable. Same thing happens with Google Meet. Azif, you were telling me about some other statistics. What was the program you were using, Azif? When you and I were talking about this the other day.
Yes, we have done some throughput test on or the bandwidth test on Teams. Teams has different categories, right? Like if you're using a HD video, that using 3.5 Mbps per second. But if you're using non-HD, it is less than 2 Mbps. So it depends on what type of video you are streaming, or what type of, if it streams only voice, it's less than an Mbps. So it varies. The throughput bandwidth varies based on what you are using.
All right. So Teams can go up to 3.5 megabits per second if you check the HD box. So that's good to know. So understand the applications and how those applications behave under different conditions. Streaming video, again, so I have a wide range here, 750 kilobits up to 15 megabits per second. So where does it fall? Where do we fall in that range? Well, basically, most K through 12 online school applications, the type of applications that online education tools where students log in, they're basically web-enabled applications. So they start out as just basically a web type application. There's some text, they can do some reading. That type of web browsing traffic is very bursty. It bursts, 1 megabit, 2 megabits per second, and it brings down some data. Students read it, people read the web page. look at your Yahoo, yahoo.com or CNN.com sometime, and you'll notice that there's a burst of traffic when you first hit the page, and then it slows down, right? So your general web browsing, these types of online education applications, 500 to 750 kilobits per second, that's all you need. But then it will burst up, right? It will burst. And as you get into some higher education, you're going to get into 4K video, and 4K video requires about 15 megabits per second for 4K video stream. So if you want to maintain that high quality, you're going to need up to that kind of bandwidth. So there's your range, and that's a little bit of the applications there. Voice calls, as Zeef mentioned, when you're just on a voice call, your bandwidth is going to be 100 kilobits per second, maybe a few hundred kilobits per second. So take a look at the applications and understand how they behave in the network, and it's going to give you a lot of clues as to what sort of density you need to design the network. So design for coverage or design for capacity, and this is something that using good design tools, Ekahau, Air Magnet, these are good tools that will help you to design for coverage and capacity, primarily capacity, but don't fall into the trap of designing for coverage. And what that means is, you survey the network, and okay, I can go here, I can go there, and then then you draw a big circle and you say, okay, there's the coverage of my network right there, that circle. And that probably is not the right coverage, right? Because if you measure the client to the edge of the network, you're going to get into that thing we talked about earlier, where the data rates are not balanced. The downstream and the upstream are not balanced. And so the result of that, when the downstream direction, the access point transmitting to the client is 200 megabits per second RF rate, maybe even more. In some cases, it could be 400 megabits per second if you're using 40 megahertz channels. Could be very high. And if the upstream is 6, 7, 10 megabits per second upstream, that imbalance means that you're going to lose packets. You're going to have dropped connections. You're going to have excessive client roaming. That client device is going to be looking for a better access point because of these dropped packets. That's going to consume more battery. And overall, it's a bad experience. It's a bad experience. You want to avoid that in any network. So don't design for coverage, design for capacity. And that means making the cell smaller, right? That means shrinking things, make things a bit smaller, move that client device closer to the access point. So when that client is within range and you get the more balance between the packets, it reduces the AP transmit power. It doesn't have to transmit at the highest power rates because the clients are closer. You get lower packet latency. Now you start to see all those good things that we talked about, the characteristics of a well-designed network: low packet latency, low packet retry rates, consistency across cells, wireless cells, and consistency within the cell. This is how you get the higher capacity network. So shrink the size of that network. And later at the very end, I'll give you the numbers that I recommend you design to in this particular cell right here. So I'll throw that up at the end of this, and we'll talk about that as well. So this applies to anything. It applies to audio, right? When you're playing a song on the stereo, and you notice that it gets weaker as you get further away from it. When NASA talks to the rover in Mars, they have to deal with this factor right here. When people try to broadcast television signals to aliens in outer space, the inverse square law applies. So, and it applies to Wi-Fi as well. So the inverse square law, let's talk about what it in a practical sense. So for any distance of r, and r could be any number, r could be 5 feet from the access point, could be 1 meter from the AP, 2r could be 2 meters, 3r is 3 meters away from the access point. For any distance of r, when you double that distance, you put it on the bottom of that equation and multiply it by itself. So the signal level equals r times 1 over that value squared. So in the case of if r was equal to 1 meter and 2r is equals to 2 meters, then you would be 2 times 2 is 4. 1 over 4 is 1/4. So your power is 1/4. As your distance doubles, you see how it happened there? As the distance doubled, the power level became 1/4 the power. As the distance goes up by 3 times, the power level is now 1/9 of the original power level. And it goes on and on. At 4R, what would 4 times 4 be? 16. So at 4R, the power level be 1/16 of the original power. So this is called the inverse square law. This is what how RF propagation are all based upon the way this law. Now, of course, you still have to factor in the materials, whether you're going through walls, doors, floors, windows, reflective surfaces. All those also apply. But the inverse square law is what we have to deal with. So really, you understand that when you see that, why it's so important to shrink that cell size, and just moving that cell in by a little bit can increase the power available dramatically, and to get that higher density and higher quality connections. So another impact of these cell sizes is in this high density design is the impact on roaming. So if you're designing for on the edges, if you're designing for coverage, and you draw the circles around your network that says this is my AP, that's my next AP, this is my network, and the circles are all just barely touching in terms of the expected range, you're going to end up with gaps. And a roaming client is not going to be able to maintain a consistent call or a consistent connection through that roaming event. You're going to drop connections at the edges. You're going to get excessive roaming scans, high battery drain. You might stay connected, but you'll hear the garbling in your ear as the device tries to roam. So again, we get that design for coverage, not design for capacity, not coverage. Then you want that 30% overlap between the cells. It gives you that balanced data rates. And so now your roaming events occur consistently, and you get a overall good experience in the network. So I'm going to remind Azif and Jonathan, you guys jump in anytime you guys want here to any comments on these issues as well.
Yeah, Darren, thank you. So one point I think I wanted to add when you said about the previous slide, right? So every R distance, right, your throughput will be reduced. So I mean the power will be reduced. So in practical, if you see a very practical sense, if R is a distance, and if you get a neg 80 dBs signals, neg 50 dBs RSSI, then if you go to R, it will be usually see negative 6 dB down, so it will be 56 kind of. So you can see every double the distance, you see a neg 6 dBm of through RSSI signal loss. When we say about neg 6 dBm, it will be the power in milliwatts. It will be the divided by 4 times, right? So every 3 dBm it will be half, so every 6 dBm it will be by 4.
I'm glad you brought that point up, because the dB scale makes it look kind of confusing. The difference between neg 50 and neg 56 doesn't sound that much, but it actually is, as you said, 4 times. So there is a big difference. So the dB scale doesn't always look as bad as it looks better than it could be. So when we design for coverage, we generally going to leave all the protocols turned on. We're going to leave B, G, we're N, A, A. So we're going to turn everything on. And what's going to happen is most of the devices, you're going to end up clustering devices down in the BG area, down in the 2.4 gigahertz networks, because of that, the circle is going to be so large, the coverage circle, and devices are going to tend to drop into the 2.4 gig. Apple devices will prefer a 2.4 gigahertz network when the signal is neg 65. Neg 65, that's in Apple's documentation. You can look it up and check my numbers on that. But it will prefer a 2.4 gigahertz access point when the signal drops below neg 65 dBm. And neg 65 is certainly not a small number, but that's what will happen. So you don't want that to occur, because the 2.4 gigahertz just does not have the capacity that we need for our networks. This is what you want. What you want to do is you want things to be clustered towards the 5 gigahertz range. You want them to be clustered up there. In fact, if you can get everything on 5 gigahertz, that is the best way to do it. So in this case, we're suggesting disable the 2.4 gig for data networks. Turn off B, turn off G, even turn off A, because you don't need those low data rates. N, 802.11n can cover that quite effectively. for the lower data rate needs and the devices that are older. But you want to try to cluster your devices in 5 gigahertz, 11AC, and of course now with 11AX as well, supporting 5 gigahertz. You want to focus on that area. So why is that so important? Well, here's why. It's just sort of an illustration of why do we see so much improvement in 5 gigahertz. Well, I got to remove my my automatic slide forwarding here. So I'm gonna have to click back a few times to make this thing stick. Okay, so when we configure the AP for high density and we look at 2.4 gigahertz versus a 5 gigahertz network, you know, using this illustration, it's a well-used illustration. It's used a lot, but it's very effective because you're spreading the devices out across more channels. So with 2.4 gigahertz, you have 3 channels that don't overlap, 1, 6, and 11. And that's at 20 megahertz, by the way. That's you're limited to 20 megahertz channels and only 3 of them, and that's just not enough. In the 5 gigahertz, we have up to 21 to 24 channels, depending upon what region you're in, right? A little more, a little less, depending upon the regions of the world. But you have lots more channels in the 5 gigahertz range, and so you're not trying to compete with other devices and as much, and you're not competing with things that are not Wi-Fi. You're not competing with cordless phones, Bluetooth, microwave ovens, things like that. So is any kind of overlap? You know, so for example, in the 5 gigahertz, if you notice there on channel 17, you see a little picture there, you see 2 cars on the same road. Is that a problem? No, absolutely not. The standard is designed, it was built to allow for devices to share the same frequency. That goes back to 1990, 1996, I guess, the first 802.11. Before they start putting letters and numbers after them, it was 802.11, and it was designed with the protocols to allow multiple devices to share the same frequency. And so it is absolutely acceptable. We just don't want the condition that we see on the 2.4 gig today with 10s to 20s and 30s to hundreds of devices trying to share bandwidth. That's the situation we don't want to see. So what tools do we have? We've talked a little bit about the applications. We talked about some of the RF. So when it comes to configuration, one of the things Cambium does with our new Wi-Fi 6 product, the XV3, we have a software-defined radio. What this gives you some flexibility, some things that you can do. You can now take the 5 gig radio, you can use it as a single 5 gig 8x8, no problem. That's 8 transmit, 8 receive antenna chains, and the 5 gigahertz band. Or you can split it up into 2 4x4 radios. And what that does is, think about what happens there when you split it into two 5 gigahertz radios, 4x4 each. You actually end up with 2 MAC addresses, right? 2 BSSs, 2 BSS IDs. And so now all of your contention issues, your clear channel assessment, all that, those protocols that are there to support multiple devices and higher density, those now are divided into 2 separate BSSs. And so that's why we can start to increase the density with multiple radios when you turn on the software-defined radio. Particularly suitable, well suited if you have a mixed network with some older technologies, 11AC, hopefully not much 11N in there, but it might be in there. You want to consider using a software-defined radio to increase the density for those older devices. And then as the next couple of years, as things move on, we can migrate to 11AX. Well, it's all 11AX, even with the dual radio mode, it's still 11AX. But now as we go forward, we can migrate to the full 8x8 mode and let the access point do all the things that 11AX is known for and all the things that it promises to do. So how hard is this to work with? So let's take a look at some of the tools that we have. And actually, you know, Jonathan, I'd like to have you sort of walk us through some of these tools here, of just to show people what we're doing to sort of start to see how simple it can be to use these tools.
Absolutely. If you're doing some design work or designing some high density networks, definitely check out the Cambium Wi-Fi Designer tool on our website. It's free and anyone can download it, or it's cloud-based, so you can get access to it and use it. But this is an example where we're able to use the Cambium Xeris unique 4 radio APs in a high density area. What we've got here is two access points deployed with these are XD4 4 radio APs, but what we're getting is actually 8 radios worth of Wi-Fi. So and with software defined radios, we can actually set the radios on each AP the way we want. So in this case, what you're seeing is we're getting 6 5 gigahertz radios in this same space and 2 2.4 gigahertz radios, but we're doing it with only 2 access points, which is pretty awesome. So the idea is we're spreading the users across those radios. We're getting a lot more throughput per user. We've got a lot less users per radio, and we're maximizing the spectrum there. Ultimately getting a lower total cost of ownership as well, because we're using fewer APs, number one, fewer switch ports, and a lot less cabling as well. So it's we're not having to turn off any radios at all with the Xeris product as well. So a lot of advantages there. And this is an example in a different kind of floor plan where right sizing is important, right? So you've got your typical low density areas in the center and the right hand side of the floor plan where a standard 2 radio AP is going to be perfect for that amount of density. But on the left hand side, you've got a kind of an auditorium style classroom where you're going to have more users. Well, let's right size and put a 4 radio access point versus a 2 radio AP in that space. And again, we can set the radios accordingly to support the 5 gigahertz clients that are connecting. So, we're getting three 5 gigahertz radios in that space for the users to use. The fixed access points, it would take 3 APs deployed in that same space to get the same thing.
Okay, thanks, Jonathan. So Jonathan, a question for you on this SDR, the software defined radio. How easy is it to use? Is this a complicated process?
It's about as easy as it can get. Actually, I've got a demo I can show, in our XMS Cloud management tool to show you, it's basically a mouse click, and you're able to switch a 2.4 radio into 5 gigahertz. It's that simple.
Yeah, I wish we had time we had set that up to do that. I would have loved to have shown people how simple it can be. We did plan for it, but didn't get that to work here this morning. But
Sure.
So, sorry, Jonathan, go ahead.
No, it's like I said, there's a XMS Demo link on our website. If you want to check that out, you can go in and select an AP, and it's literally you pull up the radios on that access point, and out of the box you're gonna have a 2.4 radio and a 5 gigahertz radio. You basically click the 2.4 and you switch it over to 5 and click save, and you've got a dual 5 gigahertz AP. Likewise, on a 4 radio unit, you have the option to switch those radios over to maximize the 5 gigahertz spectrum. So it's a great solution to solving the density requirements.
Cool, thank you. And so the nice thing about the way this works from Cambium is you can set up the network. And I encourage people to do this. And maybe SDR isn't right for every network, but you can easily test. You turn it on, test it, turn it off, run the test. It's a point and click. No special firmware to load. It's built in and allows that flexible deployment. So very easy to do, very easy to run your test and your designs and validate your network designs. So in summary, these are some things we talked about.
Yeah. So Darren, what we are saying here is we are saying when you design the high density network, we need to design for 5 gigahertz, right? And so that it will automatically cover 2.4, and in between, if you want to change 2.4 to 5 gig, you can do that as well, right? Is that what we are conveying?
Yes, absolutely. When you're supporting that high density network, we can actually redeploy some of those radios, turn them into 5 gig radios for those ultra high density networks. So kind of two basic categories: some RF planning, some configurations. Of course, we talked at the very beginning about the applications. Then we talked about some of the RF planning things. I like to survey to neg 60 dBm. My objective is to get 30 dB SNR, 30 dB SNR within that wireless cell. And that's asking for a lot. But quite frankly, we need that. We need that. The networks, Wi-Fi networks today are mission critical in every single network. There is not a single network that has Wi-Fi that does not believe it is the most important part of their network. That's the world we live in today, where there's education, retail, transportation, logistics. Wi-Fi is the technology of choice that companies are using to transition and make their businesses more efficient, to improve education. So we want higher SNR. We want higher rates, lower latency. We get that by targeting 30 dB SNR. Now what's going to happen is not every device is going to hit the 30, right? Some of them are going to hit 25, some are going to hit 35. But design it to 30 and overall you'll have the better experience. Now when you do that, you're sort of introducing a problem at the same time, aren't you? And so the next phase there, but don't forget the next step down is disable BG. And you might even disable A. Disable 11 ABG, or in the case, as Jonathan was talking about, redeploy those radios as 5 gigahertz radios, and that's even more effective. Those protocols were designed in 1999, right? That's when 11A was released. That's when B was released. Those protocols are old, and the devices today just simply don't need them. They're still there for some backwards compatibility, but we just don't need to be designing the network to support those protocols. Prune the data rates. If you prune out the data rates below 24 megabits per second, it's going to reduce the range of the wireless cell advertisement. So the packet that comes out of the AP that says, I'm an access point, it's a beacon, right? It's a beacon frame. I'm an access point, you can connect to me. That packet will not go as far when you prune those data rates. So you want that advertisement to shrink the size of the cell. When devices do connect, you want them to link at high data rates. You want to reduce those lower data rate connections, because that's going to improve the higher density, the capacity of that wireless cell. Once you start digging into the access points and the configuration of the APs, you want to enable 11K VNR. These are good smart protocols. They've been around for a good number of years. They're supported by iPhone devices, Android, newer devices, Windows PCs. They're all there. Better resource management, RF resource management, better roaming, and so you end up with an improved client experience overall. So make sure that you enable 802.11k VNR. And then automatic RF management. There's lots of tools, wireless vendors, specific optimizations. Cambium has got a bunch that will mitigate interference, assist with roaming, and select the optimal power and channel. And so enable those tools as well, and get to know those tools and understand how they can help your network to adapt to the needs of a high density network. All right, that's the material we wanted to share with you folks today. I know we kind of skipped across the top, like skipping a rock on a lake, on this topic of how to design a high density network. And so remember the objectives and what a characteristics of a good network is. Low latency, low packet retries. That's characteristics of a good high density network. So Olivia, that's the conclusion of our material today. So if there's a few questions, Olivia, we'd like to answer a few questions and then give people back a few more minutes of their day and appreciate their time.
Yes, so there's one question in the questions panel. They're asking, how does the inverse square law apply to the roaming overlapping cells?
I think I'm having PC problems. My audio is does my audio sound distorted to you?
It's a little bit
Does it sound a little jumpy? Yeah, I think I'm having PC problems today. I need to talk to IT about this. I think I'm running out of DRAM. Could you repeat the question? Because it was very garbled for me, and it's not your fault. I know it's on my side. Could you repeat the question about it? It was something about the inverse square law.
How does the inverse square law apply to the roaming overlapping cells?
Yeah. Okay. How does it apply? So the way it applies is you need to have that 30% overlap. And so Z spends a lot of time helping people pick the right values. So the inverse square law tells us how much the signal is going to degrade. And so what it tells us is that a cell that's designed for maximum coverage is going to have very little power at the edge. And what happens when the power drops out that much is that it increases packet retries. Now, I mentioned to you my audio quality is very poor, and it is, and I do have to call IT about this. But when you start dropping packets, and by the way, this is because of my PC's DRAM, not Wi-Fi. But when you start dropping packets during that roaming event, okay, it comes up as an echo in the audio. So so that inverse square law tells you that the power level is going to drop way off. The low power level is going to lead to packet retries and higher latency. Packet retries and latency will show up as an audible. You'll hear it when you're trying to roam. If you're using a data device, you may not see it on the data device because data is very bursty, and so the data may not pick up that roaming. But some applications that are more real-time applications, they will. You will see drops in the application if it's a real-time application. Azif, what numbers do you, just rule of thumb, Azif, do you have any rule of thumb numbers to share with us?
Yes, Dan, thank you. So the rule of thumb is when you deploy the roaming overlapping cells, right? So if one AP is there and AP2, when you do a Wi-Fi analyzer on AP1, you should see the BS of AP2 on a neg 80 or 85 dBm. So that will give you a 30% overlap when you roam from AP1 to AP2. So approximately neg 85, that's a good range. But if you're having more strength, then that's a problem when we talk about CCA. So to answer Darren, it will be approximately 80 to 85 dBm.
Okay, that's a rule of thumb to make sure you have some overlap between the cells. Okay, thank you. Olivia?
We also had someone asking for the SDR demo. We can send a link to that in the, can we send a link to that in the follow-up email?
We certainly can. But we were remiss on doing that. We should put it right there on the slides. We'll send that in a follow-up email.
I'm also happy to jump on a call with anyone interested to show it one-on-one. Reach out.
All right. And how does 11AX work with high density?
11AX. We didn't touch much about 11AX, did we? We kind of skipped over that, Zeef. We put it up there, but we didn't really drill into it. So 11AX is going to help high density a lot. So I'm glad you asked that question. 11AX is it gives us a lot more tools to manage multiple devices talking in the same frequency at the same time. So with 11AX, we're actually going to enable multiple communications right now from 11A, B, G, N, and even 11AC, despite put multi-user MIMO aside for a moment because it doesn't really work all that well. All wireless technology is a single talker technology. One device can transmit at a time, just one. Does it very quickly, but only one at a time. With 11AX, we're going to let multiple devices talk at the same time. It could be 3, 4, it could be 8, it could be up to 37. That's going to on the extreme end, more in the IoT space of 11AX. But we can now support multiple devices talking using the same frequency, talking at the same time. 11AX also supports better overlapping control. So we can have multiple access points sharing the same frequency and still being able to support 11AX with overlapping access points. So when those cells start to overlap, we can now even overlap the channel usage by a little bit with 11AX. So we're going to get higher density access points, higher density clients, and lower overall, a better quality experience, lower latency, lower retries.
This next question is asking, how do I know if density is an issue or if something needs to be upgraded?
Yeah, how do we know this? Azif, how do we know? What can we look for?
Yeah, actually, it's a good question. So Darren, density is an issue. So consider we deployed 11AC access point, and we were last year we were using different type of applications. But when we go to the this year, the applications have changed and the bandwidth has changed, requirement changed. But the same number of clients needs more bandwidth. So your capacity planning, whatever Darren mentioned, that when you design the network, you do a capacity planning. Basically, you do the capacity planning depends on the airtime of what the client needs it, right? So again, the airtime based on what the client needs and what application it's used. So when you change from application X to application Y, the requirement has changed. Your density requirement also is changed. So based on that, first thing is you can check with the end user, hey, how how is the Wi-Fi looking good? Is it you are getting a lot of retries, call quality, or video streaming? So we need to understand from them. And it is not 100% correct that you designed the network on last year for high density based on the airtime. When you change the applications, completely different. And the other question regarding the AX comes into picture. It's a completely different topic with OFDMA up and down. So yeah, so it needs to be. We can directly ask the customer to understand is it any retries happening, or you can check the access point logs itself to find what's actually happening in the network.
Right, so we can look at the access point, some of the counters there. We can look at retry rates. We can look at quality indicators. Then we can also talk to the clients about their experience, and these are going to be good clues about the density of the network. Thank you.
But great point, Azif. And I always kind of say, it depends. It depends on what's happening. There's a difference between an association and a user actually, pulling it down a 4K video, for example. So, it always depends on what's happening, and I always stress that if there are important mission critical applications that need to be run on the network, then your whole story behind determining what high density is changes totally. So
right,
good.
Right.
Know the applications.
Yeah.
I like that. All right, well, thank you all very much. Olivia, we're about 47 minutes in, so we can I think we can give people back an extra 15 minutes of their day, and I appreciate their time, that time they spend with us. Please do reach out if you need more questions. Azif, as I mentioned, he's a principal solution architect. He works with the software, the cloud software configurations. He works with people explaining how to architect these networks and how to use the tools to do site surveys. He does a lot of that work as well. Jonathan is one of our technical experts, but he's out there in the field helping people understand how to put this all together, right? How to put it together into a reasonable BOM that's not going to break the bank, and it's going to be light on the wallet. He's the guy for that. So we appreciate you folks' time. Please do reach out. We'd be glad to answer any further questions. Thank you for your time.